Hello students, welcome to 14th lecture of surface chemistry. So earlier we discussed about some properties of colloidal solutions. Now let's discuss remaining properties. So next is Brownian moment. So when colloidal solutions are viewed under a powerful ultra microscope, the colloidal particles appears to be in a state of continuous zigzag motion all over the field of view. So that means here we can understand it with a given example. So as we can see, we have a single particle mentioned here. In case of a solution, we have multiple these type of particles. But here we are going to discuss with single particle example, so we can understand the motion. So as from the starting point, as you can see, particle is moving in straight direction, and at certain point it changes direction, then again it changes direction, and same type of random motion and changing of direction are seen. So why this type of situation occur? Why particles changes direction? They do not change their direction on their own. Actually, during the changing in the direction, there will be a collision either with the other particle of the same type, that means colloidal particle, or wall of the vessel in which we contained our solution. So because of multiple different collisions with each other and walls, these type of random movement will be observed. So first scientist Brownian discovered this type of random movements of the particle, and during this type of change in direction, actually two different particles are changing their kinetic energies as well. That means when this first particle, let us call it A, is going in this direction, let us assume we have another particle B here. So they will collide with each other at this point, and that's why both of them will change their direction. A will go in this direction and B will go in this direction because of collision. And during this collision, they will exchange some kinetic energy. Faster particle will slightly slow down, and slower particle will slightly increase its speed. So as mentioned, this type of motion was first observed by British botanist Robert Brown and is known as Brownian motion. He actually first observed this type of motions with the help of pollens. He added some pollens into water and observed these type of random movements, and they gave it name Brownian motion. This motion is independent of the nature of colloids but depends on the size of the particles and viscosity of the solution. That means if the size of particle increases, then speed of these type of movements will be slowed down. And if viscosity of solution, that means if thicker solution is being used, then it will slow down particles as well. And thinner solutions and smaller size of colloidal particles will give us speedy movements. The Brownian movement has been explained due to the unbalanced bombardment of the particles by the molecules of dispersion medium. That means solvent particles, or in this case we are talking about colloidal particles. So dispersion medium particles will bombard themselves on the colloidal particle. That means they will collide with the colloidal particles and transfer their momentum or kinetic energy. Brownian moment has a stirring effect which does not permit the particles to settle, and thus it responsible for the stability of soul. That means if these type of Brownian motions are not observed, then only effect will be gravity. Okay, gravitational pull will pull down these particles and they will eventually settle down at the bottom of the vessel. But because of continuous transfer of kinetic energy into each other, that means bombarding by the unbalanced solvent particles, they will keep moving and won't settle down. Next is charge on colloidal particle. Colloidal particles always carry an electric charge. The nature of this charge is the same as all the particles in a given colloidal solution and may be either positive or negative. That means if we have 5 particles of colloids in a solution, then all of these 5 will be either negative or positive. They won't be in both of the form. That means some of them are positive and some of them are negative. This type of situation won't occur. All of them will carry same charge. and list of some of these particles and their charges are mentioned in the bottom. So here is a different charged particles of colloids. So as we can see, we have two different categories, positively charged colloids and negatively charged colloids. We do not have neutral colloids. Presence of equal and similar charges on the colloidal particle is largely responsible for providing stability to the colloidal solution, because the repulsive forces between charged particles having same charge prevent them from coalescing or aggregating when they come close to one another. That means if they carry same charge, then as we know, same charges repels each other, and that's why they will stay away from each other. Otherwise, if they contains opposite charges, then they will attract each other and they will form larger mass or heavy particles, and eventually heavy particles will precipitate and they will separate out from the remaining solution. The charge on the colloidal particle is due to one or more reasons. That is due to the electron captured by the Sol particles during the electrodispersion of metals, due to the preferential adsorption of ion from the solution, and or due to the formulation of electrical double layer. Development of charge on the Sol particles by preferential adsorption of ion is described below. And we will discuss about electrical double layers as well. The Sol particles acquire positive or negative charge by preferential adsorption of positive or negative ion. When two or more ions are present in the dispersion medium, preferential adsorption of the ion common to the colloidal particle usually takes place. This can be explained by taking the following example. So first case, when highly diluted solution of silver nitrate is added to highly diluted potassium iodide solution, the precipitated silver iodide adsorbs iodine ions from the dispersion media and negatively charged colloidal Sol results. So first case, as mentioned, AgI attracts I minus and can negatively charged colloidal Sol. However, when a Ki solution is added to AgNO3, positively charged Sol result due to the adsorption of Ag plus ion from the dispersion medium. That means AgI attracts Ag plus and positively charged colloidal solution forms. That means in first case we have silver iodide which attracts I minus. That means actually I minus will feel attraction towards the silver ion because they have opposite charges. In second case we have silver iodide attracting Ag plus. That means in this case silver ions will feel attraction towards the iodine because they have opposite charge. Next is if FeCl3 is added to excess of hot water, possibly charged Sol of the hydrated ferric oxide is formed due to the adsorption of Fe3 plus ion. However, when ferric chloride is added to NaOH solution, a negatively charged Sol is obtained with the adsorption of OH minus ion. Having acquired positive or negative charge by the selective adsorption on the surface of colloidal particle as stated above, this layer attracts counter ion from the medium, forming a second layer as shown below. So as we can see, we have first layer here. That means we have silver iodide attracting I minus ion because silver will attract I minus. Now our surface contains negative ions of iodine. That means surface has negative charge. That's why it will attract positively charged particles. And second layer of positive charge will develop on the surface and you will get positive Sol. Similarly, in this case, we have silver iodide attracting silver. That means silver ions will feel attraction towards the iodine present in silver iodide. And this Ag plus has positive charge and that's why it will attract iodine ions from the solution or iodide ions from the solution and it will create a second layer on the surface. This is double layer, electrical double layer, which can be seen in this image. So at the center we have silver iodide solid and it will attract iodine ions. That means these iodine ions will feel attraction towards the silver present in silver iodide. So we have a negatively charged surface. This negatively charged surface will attract second layer of potassium, and that's why it will generate a double layer. So this is how a double layer will be generated, and around this we have diffused layers. That means they are not permanent layer or steady static layers. The combination of two layers of opposite charges around the colloidal particle is called Helmholtz electrical double layer. According to modern views, first layer of ion is firmly held and is termed fixed layer, while the second layer is mobile, which is termed diffused layer. Figure 5.13 depicts the formation of double layer. Since separation of the charge is a seat of potential, the charge of opposite signs on the fixed and diffused part of the double layer results in a difference in potential between this layer in the same manner as potential difference is developed in capacitors. That means because of difference of charges, potential difference arises, and because of this potential difference, they will try to gain stability. You can understand it like this way: if you have two different substances of a same type, one having more temperature than the other. That means let us assume you have two different iron blocks, metal iron pieces. One has 50 degrees Celsius temperature, second one is at 0 degrees Celsius. That means obviously 50 degrees Celsius contains more amount of thermal energy. So when we place them in contact with each other, what will happen? Temperature or energy will flow from higher energy containing metal block to lower energy containing metal block until both of them gets same temperature. Okay, that means when they get same temperature, we can say that equilibrium is established and no further reaction will be observed. Same type of uh, consideration can be used for electrical charges as well. Potential is one type of measurement of electricity. So higher potential represents higher amount of electrical energy and lower potential represents less amount of electrical energy. So when two different electrically charged layers are in contact with each other, then they will have difference in their potentials, electrical potentials, and they will try to get stable by transferring energy from higher energy or higher electricity and potential containing layer to lower potential containing layer. So this potential difference between fixed layer and diffuse layer of opposite charges is called electrokinetic potential or zeta potential. If two potentials of insoluble material precipitates do not have double layer, they can come close enough and attractive van der Waals force pull them together. When particles possess double layer as shown in figure 5.13, overall effect is that particles repel each other at the large distance of separation. This repulsion prevents them their close approach, and they will remain dispersed and colloid is stabilized. That means if they contains opposite charges, then obviously they are going to attract each other and eventually larger mass will be produced, and we can call it precipitate, which will settle down. The addition of more electrolyte to sol surpasses the diffused double layer and reduces zeta potential. This decreases the electrostatic repulsion between the particles of large extent and colloid precipitates. That is why colloid is particularly sensitive to the opposite charged ions. Suppose at the center we have our solid. That means let us say it is silver iodide. So second layer is of iodide ions and third layer is of K plus. So we have double layer situation here. Now at the surface we have positively charged layer. That means we have K plus at the surface, second layer is iodide, and at the center we have silver iodide. So when we place negative ion in this sol, so obviously this negative ion will feel attraction at the surface because surface has positive charge here. So because of this type of addition of negative ion, it will surpasses the layer, initial layer, or we can say that it will attract the potassium ions, and a layer of potassium ion will be removed, and that's why negatively charged colloidal layer will be exposed.
and second, same type of colloid will feel attraction towards the negatively charged ion or negatively charged colloidal particle, and they will mix with each other and precipitate out. That means they will be removed from the solution. Next is electrophoresis. So existence of charge of colloidal particle is confirmed by the electrophoresis experiment. So this is the experiment where we can find the charges of the colloidal particles, whether it is positive or negative. When electric potential is applied across the two platinum electrode dipping in the colloidal solution, the colloidal particles move toward the one or the other electrode. The movement of colloidal particle is under applied electrical potential is called electrophoresis. That means, as mentioned earlier, colloidal particles may have either positive or negative charge. So when we place them under the electrical field, they will feel attraction towards the oppositely charged electrode. If colloidal particle carries positive charge, then they will feel attraction towards the negative electrode. And if they contains negative charge, then they will feel attraction towards the positive electrode. It is called electrophoresis. This can be demonstrated by the following experiment setup. Figure 5.14. So as we can see, you have an image. Here we have a U-shaped tube and we will fill our solution, colloidal solution, from reservoir. We can add it from the reservoir and then we will fill these tubes fully. On the one side we have cathode which is negatively charged and we have anode which is positively charged. So initial level is mentioned, and now when we apply electrical charge in this tube, if negative ions are present or negative colloidal particles are present, then they will move towards the anode as we can see in this image, and if colloidal particles are positive in nature, then they will move towards the cathode and they will settle down on the surface of respective electrodes having opposite charge. When movement of a particle is prevented by some suitable means, that means semi-permeable membrane. If we place semi-permeable membrane in the way of colloidal particle, then they are not able to pass through it. So at that time it is observed that dispersion medium begins to move in electrical field. This phenomenon is termed electroosmosis. Okay, so remaining properties will be discussed in next lecture.